Okay, we're going to be looking at practical applications of maximum and minimum problems. So we can use differentiation to find the maximum and minimum of a function in practical situations. For example, if there was a manufacturer and a canned food company, that manufacturer wants to minimise the costs in the manufacturing process. So they would look at the amount of metal they need to cut out to make their cans, and they know they want to make their cans to be a particular volume. Well, they can use they can find the maximum minimum of the formula to involved in the surface area and the volume of that of the shape that they're making their cans into, and it can help them to maximize the efficiency of the product that they're making and minimize the waste. Let's see what we mean by that by doing a few examples to show you how this works. So the surface area of the solid cuboid is 100 centimeters squared, and the volume is V centimeters cubed. So let's draw our cuboid. Oh dear, it's terrible. And this length here is x centimeters. This is also x centimeters, so the top and bottom shapes on our cuboid are squares, and it's h centimeters high. First thing to note, everything is in like units. So we've got centimeters squared for the solid, surface area. We're thinking about volume in centimeters cubed, and the dimensions are given in centimeters. If any of these were different, like for example, some was in centimeters and some in meters, you would need to bring them all into the same unit. So, firstly, express h in terms of x. B. Show that the volume is given by 25x minus a half x cubed. C. Given that x can vary, find the stationary point, I'm sorry, it's SP for stationary point. Find the stationary point value of V and determine whether this stationary value is a maximum or minimum. So, firstly, express h in terms of V. So we know the surface area is 100. So what is the formula for the surface area? So the surface area is going to be the top square. It's going to be all the different shapes added together. So we've got the top square and the bottom square are x squared each, and there's 2 of them. And now we've got 4 of these rectangles on each side, so that's going to be x, h, and there's 4 of those. And so 2x squared plus 4xh is going to be 100. So next step is we need to rearrange this formula. So we make h the subject. So we'll have 100 minus 2x squared is going to equal 4xh, and 100 minus 2x squared over 4x is going to be h. So, and now we're going to break this into two fractions. So I'll put h on this side. So it would be 100 over 4x minus 2x squared over 4x, and simplifying that down, h will be 100 divided by 4 is 25 over x minus, so the 2 is going to cancel and that x will be cancelled, so it's going to be half x there. Now, second part is show v is equal to this. So what is the formula for the volume? Well, the volume is the area of the bottom, so it's x squared times the height. So we're going to, but we know this is what h equals, so we can substitute this in for h. So we'll have x squared multiplied by 25 over x minus a half x. So that's going to give us 25x, that x squared, that x will cancel out one of the x's here, minus a half x times x squared times x is going to be x cubed. And that's what we wanted to show. When doing this, just you can just put a wee note saying substitute for h, and then just to make it clear what you're doing. Now I'm going to run out of space, so I'm going to get a new, I'm going to clear that away and get a new bit. So C, so we have for our volume 25x minus a half x cubed, and given that x can vary, find the stationary point value of v and determine whether the stationary point is a maximum or minimum. So when you hear stationary point, you should automatically think derivatives. So we're going to differentiate this with respect to x. So that'll be 25 minus 3 over 2 x squared. So stationary points occur when dv by dx equals 0. So 25 minus 3 over 2 x squared equals 0. And if we rearrange that, we'll get x is going to be 5/6 over 3. So when x is 5 square root of 6 over 3, v will be, so we'll put this back into here, 25, and that's going to be 5 times the root of 6 over 3, minus half 5 root 6 over 3, and that's all going to be cubed, so that's going to give us 68.04 to 2 decimal places. And the second derivative of this will be, let's look at where's our first derivative, here it is here. So that won't have anything, so it'll be minus, bring it 2 down, it's going to cancel with that, minus 3x. And when x is 5 times the root of 6 over 3, the second derivative is going to be minus 5 root 6, which is less than 0. So the stationary point of V is 68.04 and it is a maximum value. So what does that actually mean? So the maximum volume that this cuboid can take is 68.4 centimeters cubed. That's the maximum value of this volume, and we have that volume when this value for x is 5√6/3, so centimeters. So when x is this, we get a volume of 68.04 centimeters cubed. Let's try another one. So we're going to draw a sphere. This is meant to be a sphere. And in our sphere, there is a solid cylinder. Let's try and draw this. Oh dear, it's a bit rubbish. Okay, and it has radius r. So the radius of the cylinder is this. It comes out to here, to this side of the sphere, and we have the centre of our sphere out to here. That's 5. Oh no, that's 5 centimeters. So that's the radius of the sphere, and the length here is 2h. So the diagram I'm actually going to make that a bit clearer. I'll do this length here, so you can see the height of the cylinder is 2h. So the diagram shows a solid cylinder of radius r and height 2h centimeters, cut from a solid sphere of radius 5 centimeters. The volume of the cylinder is c centimeters cubed. Firstly, express r in terms of h. Secondly, show that the volume is equal to 50 pi h minus 2 pi h cubed. C, find the value of h for which there is a stationary point. And finally, determine its nature. So, firstly, express the radius in terms of h. So if we look here, this is, if we look here, that we've got r here, and we've got, this is 5 centimeters. Now this here, from here to here, is half of the height of the cylinder. Half of the height of the cylinder is h, because the whole height of the cylinder is 2h. So now we've got a right angle triangle. So we can use Pythagoras. So we want to find out what r is in terms of h. So r squared plus h squared is going to be 5 squared. So r squared will be 25 minus h squared. So r will be the square root of 25 minus h squared. And a lot of these kind of examples, you will be looking for little, look for triangles and shapes. If you find triangles, you can think Pythagoras. You might have questions where, like in the next problem, we're going to look at where it's similar shapes. So you're looking for these little things that can be the key to unhooking the problem. So B, show that the volume is equal to this. So the volume of the cylinder, what is the volume of the cylinder? The volume of the cylinder is the area of the circle at the top times the height. So we're going to have pi r squared times 2h. Now we know what h is because we've just worked it out. So it's going to be, I mean we know what the radius is because we've got it here. So the radius squared is 25 minus h squared, and we've got this 2h here. So let's expand the bracket. So we will have 2h times 25 is going to be 50h, and we've got this pi here, and it's going to be minus 2h cubed, and there's the pi, I'll put the pi in there, and that's what we have here. And then C, find the value of r for which is a stationary point. So we're going to differentiate with respect to h. So it's going to be 50 pi minus 2 times 3 is 6 pi h squared. At the stationary point, dv by dh will be 0. So we'll have 50 pi minus 6 pi h squared equal to 0. So h squared will be 50 pi over 6 pi, or h will be 5 root 3 over 3. And finally we want to find the nature of the stationary point. So to find the nature, we'll do the second derivative. So here was our first derivative here, so that's going to be minus 12 pi h, and when h equals to 5 root 3 over 3, d2v by dh squared will be minus 12 pi 3 over 3. Therefore, it's less than 0, so it's a maximum value. And we're going to do one more example. So again, we're going to do a diagram of a cone this time. And inside our cone, we have another cylinder. Now the radius, let's put a V, is going to be r. and from the centre to the outside part of our cone is going to be 12 centimetres. Now the height of our cylinder is h, and the height of our cone is going to be 24 centimetres. Now where you have cones, think either Pythagoras or similar triangles. The diagram shows a hollow cone with base, radius 12 centimetres and height 24 centimetres. A solid cylinder stands on the base of the cone, and the upper edge touches the inside of the cone. The cylinder has base, radius r, and height h, and volume v. Firstly, express h in terms of r. Show that the volume is equal to 24 pi r squared minus 2 pi r squared, cubed, sorry, not squared, cubed, and find the volume of the largest cylinder that can stand. Oh, look what I'm writing there. Inside the cone. So, what we're going to use here is similar triangles. So remember, with similar triangles, there is a scale factor. So the radius of the cylinder is r, and the radius of the cone is 12. So r over 12 will be the scale factor for similar triangles. So if you were to draw a triangle inside here, the triangle here is a similar triangle to if you were to draw the triangle from the centre to the outside of the cone and up here. So that triangle, I'll change the colour so I can show you what I mean. So this triangle here is similar to this triangle here. Okay. So the scale factor for the radius, the bottom part of the triangle, this line here, will be the same as the scale factor for the height of the triangle. So the height of the triangle for our big triangle is going to be 24, and we're going to actually use, there's another similar triangle in here, this one here. So we use this one, so it's going to be 24 minus h. Oh, I've got my black back. So I want to rearrange this so that we're making h, so that's meant to be a minus there. So 2r is going to be 20 is equal to 24 minus h. So h is going to be 24 minus 2r. Now we know the volume of the cylinder inside is going to be pi r squared h. So that's going to be pi r squared, and h is 24 minus 2r. So we expand that out, we will get 24 pi r squared minus 2 pi r cubed. And next we're going to take our volume for our cylinder and differentiate it so we can find the stationary points. So we have V as 24 pi r squared minus 2 pi r cubed. dV by dr is going to be 48 pi r minus 6 pi r squared. So stationary points occur when dV by dr equals 0. So 48 pi r minus 6 pi r squared equals 0. So let's factorize this. So we're going to take out 6 pi r and be left with 8 minus r equals 0. So r must equal, well, the radius can't be 0. If the radius is 0, then there's no cylinder. So r must be equal to 8 centimeters. So when r equals 8, V is going to be, if you plug that back into our volume and do the maths, we'll get 512 pi is the volume of the cylinder. And we want to determine the nature of this stationary point. So the second derivative of the volume will give us 48 pi minus 12 pi r, and when r equals 8, the second derivative will be equal to 48 pi minus 12 pi 8, which is less than 0, so the stationary point is a maximum. So therefore, the largest volume the cylinder can take is 512 pi centimeters cubed. So I hope that helps.